I'm very happy to be here. Actually, I came here in Oxford in 1996 as a very young PhD student. And I think I discovered here how important it is to be curious about everything around you and how can science bring you information and explanations about things that you watch, that you wonder about. And this book was after working for about 10 years on sports and modeling of sports. So the first chapter is about understanding running and how you should go running, how you can run with math and understand what is the best way to run that I will describe. And this book is full of questions that you can wonder about. Some of them you may know the answers, some of them you may not. And the idea of this talk is to present a few questions and a few answers. So the first question is for you. Maybe I won't take the answers because there are a lot of people here. What is the fastest sport? I don't know if you have any ideas. So the answer is badminton. So I'm sorry for the distances. I'm still thinking in kilometers per hour. But what you have to remember is that golf balls and jai are very quick as well. Sometimes people think that table tennis is very quick. It's not that quick as you see. It's down, down, below. Though the ball is very light, we'll see that it's smooth and it's very different from in terms of air resistance. So the other issue is who are the fastest athletes? So they are not people with cars. They are not people coming from the sky. They are people, you don't find so many in England because you don't have these steep slopes, but they are downhill skiers. They can go up to 250 kilometers per hour. If you want to jump from sky to reach this velocity, you would need to jump from far away in space. Because when you jump, you have this spread eagle position. And because of the spread eagle position, the resistance of the air is very important, very big. And therefore, compared to the downhill skiers who has a tuck position, they go more slowly. Another question which is related to things that I will say later is which sport requires the fastest reaction speed? Very good. This is the first time someone gives the correct answer. So it's either tennis or baseball, because balls are very quick and you have about 30 to 40 milliseconds to decide whether you go on the left or on the right. Now, the fastest wheelchair athletes outstrip the able-bodied, but there's something very strange, is that for the 800, 1500, 5000 and marathon, they are run more or less at the same average speed. But the marathon itself, they go more quickly in average speed than the 1500. Do you have an idea why they can be quicker on a marathon, which of course for able-bodied is not true at all? Well, the answer is related to the French title of my books, which is Why Julian Bend, because marathon are in cities, so there are not so many bends, and wheelchairs are very slow when you have to turn. So what about bends? Actually, if you go back to ancient Greece, in ancient Greece, there were no bends. They were running back and forth at that time. So very bad for performance. Actually, the name stadion, which gives the French stade, is both the name of the track and the name of the shortest race, which was around 200 meters. 200 meters was the size of a foot, of a god's foot at that time. And so the shortest race, you were just doing one way. And the others were going back and forth, so very bad for performance. But at that time, that was not the problem, because in order to honor gods, you had to be the first. And so there were no way to measure time, no way to measure distance, and they didn't really care about stopping and having to go backwards. So it's with the Romans that appeared the circus with the horses, and from movies that bends were really a problem because they were tight, and this was a difficulty. And the issue is when you have bends and you go very quickly, then the quicker, the more inclined you have to be. And the issue is, what about runners? Of course, runners don't go as quickly as speed skaters, but nevertheless, they bend about 10 to 15 degrees for sprinters. And they lean to the left to go against what is called centrifugal force. So I would like to say a few words about what is centrifugal force. If you go in a train that goes very quickly, you will realize that when the train is turning, you have to bend because you want to stay and not fall down. And this is where the centrifugal force comes into play. That is, it will take you away because your body has some inertia. Your body would like to stay where it would have stayed if the train hadn't turned. So it's staying on the outside of the band. And the point that I was to insist on, and I'm giving you the only formula of the talk because you will see it's a practical information for Stade de France and the Paris Olympics, is that the centrifugal force is proportional to the velocity to the square and inversely proportional to the radius of the track. So it's really important to remember that if the radius changes, then the centrifugal force changes. So the smaller the radius, the bigger the centrifugal force. And for a sprinter like Usain Bolt, if you do a small calculation, actually you realize that the centrifugal force is about a third of the weight. The weight is the force that is holding you on the earth. So a third of the weight is something really to take into account when you want to analyze performance. So the issue that I've been thinking about in my research is the following, is when you go running, you fix a distance, 100, 200, 400, 800, 1500, 10,000. Actually, we didn't go up to the marathon. We stopped at 10,000 meters. And how is it that you can optimize your effort to reach the best time, to be the champion, to win the race? So, of course, like everything in life is a kind of economic decision that you have to make. It's a matter of choices and constraints and decide what is best for you. And in order to do that, we've introduced a problem made up of equations that rely on three physics laws. The first one is related to Newton's second law of motion, so it's mechanics, saying that the variation of your velocity depends on the force that applies on you. The second one is energy conservation. That is, you breathe, you get oxygen, you eat, and from nutrition you get energy as well, what is called anaerobic energy, the one that doesn't come from oxygen. So oxygen is very nice because the tank is infinite, the nutrition, the tank is finite, but both of them, they contribute to your propulsive force, and the power developed by the propulsive force has two origins that, and hopefully nothing is lost too much in this process. So you have energy. And the third equation comes from the fact that neither of you in this audience is a robot. You all have a brain, and you run and do sports with your brain. And this is very important. That is, when you go running, when you go doing gymnastics, tennis, baseball, whatever, journalists said, go with the mental, with the motivation. Actually, there is something that is going on, is that for muscle contraction, you have to decide, your brain has to give an information to the muscle to make an effort. If I tell you to get up to stand up and sit down and stand up and sit down 10 times. It may not be that energetic in terms of energy consumption, but you may find this very boring in terms of motivation. And the reason is your brain is going to give a lot of information to your muscles, but you don't find this very satisfactory. So this is where the third equation comes into play, what is called motor control. That is something that we developed working with neuropsychologists in Paris, working with patients with what is called dopamine deficiency. And for this, they understood how to model a propulsive force with respect to effort. And effort is related to the fact that you don't want to vary your force too much. And as soon as you vary force, then this is tiring. And this is something that you can relate to motivation. And motivation can play in three directions in sports. The first one, if you're motivated, you're going to be able to produce an intense effort, very intense. If you're motivated, you're going to be able to react very quickly. And if you're motivated, your brain can decide that hurting is not a problem and that you go on, though it's very hard, very tough, very tiring. And of course, this part is very important because when you think of how to do more than what you can do, then you can think of medicine that act not only on oxygen consumption, on nutrition, etc., but they can act also on your brain so that you're not really aware that it hurts too much. So we put all this into equations, and we don't measure anything on sports people. We have very precise data that is position every 100 milliseconds, that is position of the athlete 10 times per second. And with this, we are able mathematically to compute a kind of digital twin of the athlete and understand how champions for the moment or students in École Polytechnique run. And the point of this digital twin, of course, is once we have data, we're able to change the twin and say, okay, I put him running on another track. I imagine that he improves his training and improves his VO2, his running economy, his whatever. How is it going to change the performance? So first question that we are able to answer pretty easily is how you run a sprint. So for instance, 100 meters. I put you here the data of the Paris 2024, but it's the same for all sprints. It's the same for Hudson Smith for 400 meters. Athletes do not cross the finish line accelerating, but decelerating. So I don't like to say slowing down because it gives the impression that they stop their effort. It's really decelerating. And if you look at this curve here, you will notice that the maximum of velocity is really long before the finish line because it's around 60, 70 meters. All sprinters, Usain Bolt or whoever you want, they keep accelerating up to 70 meters and then they're not able to accelerate anymore. And this is true on the 400. On the 400, they accelerate up to 60, 70 meters and they do the rest, that is 330 or 340 meters decelerating. Why? Why is it the best strategy? Well, it's the best strategy because you have a brain, and the best way to do an intense effort is like if you want to destroy the door of the going out, if ever there is a fire, the best way to do it is to push very strongly, very intensely, very shortly. You're not going to start pushing more and more and more and more. We realize that the best intense effort is to do something very strongly. And this is the same for running. If you go running very strongly, the best strategy, and we managed to compute it mathematically, is to start with the most intense force that you can use, that you can produce. And of course, this force, you cannot maintain it for 10 seconds. What you could maintain is a smaller force. But if you do a smaller force, the final time would be much bigger. So the best thing is to produce the biggest force that you can. And this biggest force, because you have a brain and information coming from the brain, is going to be intense, and then the force is going down. And this is why the sprinter can only accelerate for 60, 70 meters, and then the velocity is going down. And starting slower and accelerating all along would produce a bigger finite time. So here I've put simulations for the 400 just to show you. So the red is Hudson Smith. That was in the 2022 Munich World Championship. The blue is Femke Bol, just to show you that they accelerate up to 60, 70 meters, and then they go down. Hudson Smith, he goes up to nearly a little bit than 11 meters per second, and he ends up at 7 meters. So it's not a matter that they slow down really, it's just that they cannot maintain this extreme velocity that they produce at the beginning of a sprint. And a friend of mine sent me an information about the Tokyo World Championships that ended up last week, where the 400-meter champion didn't manage to break the record held by the German champion Koch. But it was said she's going very fast because she was going much faster for the end of the race. So when you see this, you understand that it's not she's going faster, it's just that she's decelerating less. And people in the old days, they were starting very, very strongly. And now the 400 for women tends to be with a smaller deceleration than it used to be before. So another issue is, why does running behind someone allows you to improve your performance? So this is something that people have measured for a 400, that is a lap. If you go behind someone, not me, I say you, maybe you, at least not me. But let's say Hudson Smith or whoever running properly goes behind someone who gives him the right spacing, he can earn 1 second. So 1 second is a lot on a 400. The reason is this psychological. That is, if you see someone before you, you don't have to think about what you're doing, you're just following. So it's like you're attracted, you're attached to the person in front of you, and this reduces the effort that you have to produce. It doesn't reduce the energy, because it doesn't change the energy, but it just reduces the mental activity that you have, and therefore the effort, that is all the transmission of information between the brain and the muscle, is reduced, and it allows you to keep energy, effort for the end of the race, and therefore get to a bigger time. If you want to be convinced of that, you have to imagine if you go to a new city and you go from one point to another, the first time you look everywhere, and when you're on the way back and you recognize streets or monuments, then you will have the impression that the way back is a little bit quicker. It's just because your brain is working less. And when your brain works less, then your activity, your effort can be bigger. So it's the same for runners, it's the same for all sports people, and especially so when you are on a track with 8 lanes, we have managed to compute what are the best lanes. So of course the problem with the outer lanes is that you're running blind. The problem with the inner lanes is that the centrifugal force is very strong, because as I showed you at the beginning, the centrifugal force is inversely proportional to the radius. So the smaller the radius, the bigger the centrifugal force. And in the end, the best lanes are for standard tracks are lanes 4, 5, 6, 7 and 3 or more or less equivalent, 8 and 2 or more or less equivalent, and lane 1 is terrible for performance. So there's no hope to see a winner in lane 1 because of that, and also because the draw favors the center lane, that is, the 4 best are put in the central lanes. So in the end, the winner is always there. So we have been working on the 1500 for quite some time, and analyzed especially Inge Brixton, and the point of our studies is that we manage with our digital twins to get back information about things that you cannot measure, and especially VO2, that is the rate of oxygen you transform into energy. And we were able to analyze this because we had a lot of data for Inge Brixton. So I'll just show you the kind of curve that we're able to produce. This is the velocity for a 1500. And we managed to imagine, okay, imagine that he has a bigger VO2, that he has a bigger force, that he has a bigger whatever. How does it change performance? And what we understood is that Inge Brixton is someone who had a very good VO2 kinetics. That is, the rate of oxygen that he transforms into energy starts very quickly. Because of that, it means that he doesn't have, so maybe I should explain, this is the velocity versus the distance. So at the beginning, they always start the 1500 accelerating a lot more than the mean velocity or the real pacing that they are going to follow. Why? Because this is the best way to start the oxygen system quickly. So the point is, Inge Brixton has a very good kinetics. So normally his best way to run is to stay behind. This is how he wins, because he stays behind, which has 2 advantages. The first one is that he's taking into advantage the fact that he's behind. And the second one is that he has his kinetics starting quickly, so he doesn't need to spend anaerobic energy to do a quick start, sorry. And the point is, then he, on a 1500, they start accelerating on the last 2 laps. The last 2 laps are run a bit more quickly than the second one. And the point is, what happens now if, as in Paris 2024, he starts first? Well, what happens is that Josh Kerr is coming from the outside, Cole Hocker is coming from the inside, and normally, if the track had been a standard one, Cole Hocker should never have been able to win because of the centrifugal force. And what happened is Cole Hocker won, and he said, I don't know how I managed to do it. Sebastian Coe, the former 1500 champion and president of World Athletics, said, I don't know how he managed that. And nobody said it at that time, but I give you the information. The information is that the Paris track was not standard. So you're going to tell me, okay, the French, they always do things differently from the others. Yeah, that's not completely wrong. The issue is the following, is that on Stade de France, they often play rugby. And they had this rugby pitch. And in order to encompass the rugby pitch, you cannot have a standard track. So what do I mean by a standard track? All tracks, all athletics tracks are 400 meters long. No problem. The issue is you can vary the length of the straight and the radius of the bend. So the standard tracks, the radius is 36.5 meters because twice times 36.5 is 73. That's the width of a football track. So if you want to encompass football, you do a standard track, 36.5 meters for the bend, and this gives you, with the 400 calculation, the length of the straight. Now, if you want to have rugby, you have to do something else. In the old days, they were building what is called double bend tracks, which is very bad for performance, which is the case of the Berlin track, for instance. But in Paris, they did something else, which is the same as Monte Carlo, is they decided to do a bend which is a little bit bigger. So instead of 36.5, they have 37.5, 1 meter, not much. But when it's in terms of centrifugal force, where we divide by the radius, and they are going at velocity which are of order 6 or 7 meters per second, then this is where you can earn a hundredth of a second. And so it means the bend is a little bit bigger and the straight is a little bit shorter. So it's very different from performance. I'm working on that at the moment. It's showing exactly how it made a difference, and especially on 200, 400, 1500, it was impressive that a lot of athletes have beaten their personal best. So if you try to do statistics, of course, on 8 people on a final, then you're going to say, okay, maybe 5 or 6 have beaten their personal best, and so what? It's the Olympics, etc. But if you go to the digital twin model and you realize that the digital twin is earning 0.1 or 0.2 seconds because of the track, then you understand things better. So this is what happened, is that Cole Hocker was in the inside, but in the inside the centrifugal force was a little bit smaller than on a standard track, and what he could never have reached on a standard track, and Josh Kerr coming from the outside should have won, because it was slightly different. Cole Hocker managed to win. So let's stop about running and move to other sports. So I've put a little bit of cycling. Why on a bike? The faster you go, the more stable you are. And I put this quotation by Albert Einstein: life is like a bike. You have to move, not to lose your balance. So the issue is, if you have kids, or if you are a kid and you started biking, it's very difficult at the beginning because you have the impression you cannot find your balance. The handlebars are moving left and right, and you have the impression that you can maintain the handlebars more or less straight as soon as you reach a high velocity. But of course, when you're starting biking, or when you're in Paris on a Vélib, which is very heavy, it's very difficult to start with a big velocity. So the explanation is again related to centrifugal force and related to equilibrium. So if you turn your handlebars, you realize that you increase the area of equilibrium. The idea is the following: when you have the system, which is the bike and the human being, it has a center of gravity, which is more or less the center of mass. In order to be at equilibrium, the center of gravity has to be above the geometrical figure that you obtain by joining all the points in contact with the ground. So if you turn the handlebars, this increases the size of this figure and you have more positions of equilibrium. If you have seen clowns at the circus, clowns used to have, I say used to because in France, I don't know about Britain, they have forbidden animals in circus, so there are fewer and fewer circuses. But at least clowns used to have very long shoes. And with these very long shoes, they could, no, Daryl, I'm not doing it, I'm not falling down. They could bend a lot because the center of gravity could go, you know, if my shoe goes until the end here, then I could bend a lot because my center of gravity will stay above my points of contact on the ground. So it's the same for the bike. When you turn the handlebars, you increase your equilibrium in some way. But on the other hand, if you fall down, then you're producing a centrifugal force. And as we said, it's proportional to the velocity and inversely proportional to the radius. So what you have to think about is that if you turn the handlebars a lot, then you're going to do a very small circle. It means you need a small velocity. And if you have a big velocity, this allows you to a big radius, and a big radius is close to the straight line. So this is why you have to go to a large velocity in order to not to turn the handlebars too much. So another question related to basketball: why do basketball players seem to hang in the air? Michael Jordan is often said to fly. The reason is the following, is again the center of gravity explanation. Is when a basketball player is jumping, his center of gravity is following a curve which is in red here, which is called a parabola. The point is, when I move my arms, for instance, if I raise my arms, then my center of gravity is going to move up on my body. The same if I fold my legs, my center of gravity is moving up on my body. So if at the same time as the center of gravity is going up here, the player move up his legs and move up his hands, and fold his legs, then it turns out that the center of gravity is following the parabola, but the head is staying at the same level. And because what you're watching is the head, because on TV there's no arrow or cross to indicate the center of gravity, so you're just watching the head, and impressive, the head stays at the same height. So he's flying, just a physics effect. And it's the same for ballet dancer. When they do a grand jeté, they raise their arms at the top of the parabola, which gives the impression of flying, of staying with the head at the same level. So you can practice that now and give the impression of flying to your neighbors. Let's go to throwing. Again, when the weight is dominant, that is, there are no effects, the trajectory of whatever you throw is a parabola, and the longest range is reached for the middle angle, that is 45 degrees. This is not the case for golf, for instance, where the optimal angle to throw very far is about 26 degrees. And the reason is there are effects due to the air. So for small or light objects, air resistance, what is called drag, slows down movement. And the reason is that when the ball, the table tennis ball on the top is moving from the right to the left, it encounters the air, and the air is going to make vortices or turbulence behind it. The smoother the ball, the bigger the turbulence. And this is why if you have a ball which has defects, which has irregularities, then it will move more quickly. The resistance of the air will be smaller because actually the little vortices that are formed around the ball, they are going to produce like a skin of air around, and the ball will be able to move more quickly. So this is what happens with a tennis ball that has hairs, and with the golf balls that has dimples. And actually some people have investigated how the dimples should be constructed, what is the shape, what is the depth, what is the angle. It turns out that there's no math proof about that, but experimentally the dimples shouldn't be too deep, rather shallow, but the angle of transition should be large. And no one knows exactly whether it's better to have between 250 or 500 dimples. So if you take two brands, they will have a honeycomb structure, which is slightly different in depth, etc. But the point is they have dimples. And the drag, instead of being proportional to the velocity to the square, is only proportional to the velocity. And therefore, you can shoot a golf ball, much larger with a biggest range than ordinary, I would say, balls. So this is why, if you remember at the beginning, the golf ball was one of the quickest objects that you can throw. Nevertheless, if you decide to throw it at a very large angle, of course, it will go with a very different trajectory, which is called tartaglia, where it's going up, but at some point you have the impression, if you have seen champions in golf, that the ball is falling almost vertically. That's because it's a situation where the weight and air resistance more or less compensate, and this is where it falls down. I like speaking about France. So what about Tour de France? It's really well known that, being behind is best when you go running. I've explained you it's not only a matter of air, but of course, when you go cycling, it's really much better to be behind, not only because of psychological reason, but also because of air, because if you have someone in front of you, then you're protected and it's less effort, etc. What you may not know is that the first one is better for him to have someone behind instead of biking alone. So if you go biking, if you decide to be the first, check that there is someone behind you, because it will be less effort. And the reason is that, when there's air, there are vortices behind you, and if you have someone, then it takes the place of the vortices and it reduces the drag. So what happened, for instance, in London in 2012 at the Olympics is that they heated the velodrome in order to reduce the drag, because at 28 degrees, the drag is reduced. And what happens on Tour de France is that when someone leaves, I don't know if you've noticed, he's never going alone. There's always a car behind with 6 to 8 bikes on the top that is following at a very precise distance. And the reason is that some Belgian mathematicians have done the computations. If you have a car with 6 to 8 bikes behind, this reduces the drag. So nothing in Tour de France is left to something that is not computed. Football, you know it. Bend it like Beckham. If you rotate a ball when you shoot it, then it will change its trajectory. That is, if you want, I'll show you to do this. The only thing to do, and this is where you have to be good at it, is at the same time that you send the ball, you have to rotate it. Because if the ball rotates, then on the top, the velocity of the ball will meet the air counter going on the other way, whereas the bottom of the ball, you see that the velocity is the same as the velocity of the air. So there will be a difference of velocity between the top and the bottom. And there's a law in physics which is called Bernoulli law, which tells you that a difference of velocity creates a difference of pressure. And a difference of pressure means a force, and a force perpendicular to the velocity of the ball makes a spiral trajectory, and it does this. Of course, it never goes into the spiral at the end, because there's something to stop the ball, but this is how you have to imagine the physics in. Okay, so my last question is about swimming. Because we have a very good swimmer in France, so I like ending up with this, and especially he's very good at swimming underwater. But actually the question, why do you swim faster slightly underwater, came from my own experience as a moderate swimmer. And in my swimming club, there are a lot of kids learning to swim, and I always hear the parents saying, but take your head out of the water, take your head out of the water. And it always makes me laugh, because their kids are not going to drown. And if they swim slightly underwater with more or less the equivalent of a body above them, it's because naturally they find the best way to swim, because this is the best depth to swim, is slightly, slightly underwater. This is where the water resistance is the smallest. So if you see people swimming slightly underwater, just think that they must have a good intuition of what is going on, or they must have do some physics in it to understand what is going on. So the idea is the following. When you have you're swimming, the water is slowing you down for, again, what is called drag, and is made up of 3 components. The first one is what is called pressure. That is, the water is pushing more in front of you than behind you, and you want to be as horizontal, as hydrodynamic as possible. The second component is friction, skin friction. That's why professional swimmers put swimming caps, they shave. At some point, at some time, they used to have swimming suits that mimicked shark skin, because it flows better. And these 2 components, they are smaller when you're underwater than when you're at the surface. And the last one is the wave drag, which is 30% smaller when you're underwater than on the surface. That is, when you swim, when you move, you produce waves. And these waves, they are going to slow you down, which is different from the pressure drag. It's really the waves that you're producing. So all this makes that it's better to be underwater than on the surface, but of course the issue is, how do you swim underwater? So there's a nice way of swimming which is called dolphin undulation, and the perfect way to do the undulation is to create actually a thrust with an undulatory motion. You create little vortices behind you that are going to push you, because if you undulate well enough, they're going to push you exactly on your body and propel you with the undulatory movement. So what is to be known is, a long time ago, some people managed to break records doing 50 meters underwater, but that was forbidden in competition, and now it's only 15 meters authorized. And this is really something important in optimizing your swimming, is doing this undulatory motion as well as possible in order to win time on this part of the race, which is the best one. And this is where our French swimmer Léon Marchand is very good. So before I conclude, I should say something else about the Paris Olympics, is that, okay, we had a strange track, but that was pretty good. But we had a strange pool that was pretty bad. And the reason is the following, is that in 2008, the regulations changed about the depth of the pool. So 2008 in Beijing, I don't know if you remember, this was the time of the swimsuits that look like shark suits, shark skin. And at that time, everybody was saying, okay, they swim very quickly because they are like sharks. But there was another reason that was less advertised, is that 2008 was the date when the depth of the pool was increased. 2008, depth of pool authorized was 3 meters. And 3 meters is very good because when you produce waves, they reflect at the bottom, but the bottom at 3 meters is far away, so they don't have time to come back and slow you down. Well, in Paris, what happened is that, you know, sports and science are things that are very separate. So they thought 3 meters deep, that's going to cost a lot of money because the pool was a temporary pool. It's going to cost a lot of water, and we want to be ecological. So we'll do the minimum authorized, 2 meter point 10. 2 meter point 10, what happened, Adam Peaty went for his 100 meter breaststroke, and I don't know if you followed that, he did 1 second more than 3 weeks before. And it was the same for the first 3 swimmers in the 100 meter breaststroke. They all did more or less 1 second more than 3 weeks before. And this is how they started asking, but what happened? What is wrong with this pool? And what is wrong was that it was not deep enough. And professional swimmers now, they really produce a lot of waves. And at 2 meters, the waves reflect and slow them down. And they were aware of that. So my conclusion is, don't do like the French in sports. Practice science. Ask questions around you. Just watch the world around you and try to understand what is going on and improve your curiosity. And there are a lot of things that you can understand with some physics and some mathematics. Thank you very much.